All right, guys, Mr. Antonucci here, and in this video, we're going to talk about how to find the derivative of a polynomial function. And first, we're going to start off with just finding the derivative of a constant function. Now, we've been using the limit definition of the derivative up to this point, but this can become a very tedious exercise, especially for more complicated functions. So we're going to look at some basic properties for derivatives. But before we do that, I want to talk about some of the most common notations used to notate the derivative. This first one is f prime of x, and that's the one that we're mostly used to at this point. There's also y prime and also dy dx. Sometimes that's written like this, d dx with a y here, or sometimes d dx f of x. A less common notation is called operator notation, and that looks like this, d f of x, and that's used as like an operator. That means to perform the operation of the derivative. And so this would be equal to d sub x of f of x. We're not really going to use this notation at all in this course, but just wanted to bring that up in case you see it at some point. So for the derivative of a constant function, we first want to look at the graph of the constant function f of x equals a, where a is any real number. One thing that's very important to notice is that the graph of a constant function is a horizontal line. So if we have y equals a is the horizontal line, no matter where I pick on the graph is horizontal, meaning its slope is equal to 0, or its instantaneous rate of change is equal to 0. Instead of having to do the limit definition all the time for a constant, if you're differentiating a constant, the derivative is just equal to 0. Now, I'll run through the proof with you because it's very, very quick and very, very easy. If you have f of x equals a, where a is any real number, so it's a constant function, then the derivative is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. And then we have, so f of x plus h, no matter what you plug in for x or even x plus h, the constant always has the same value. It's just equal to a. And then minus the f of x is always a. So no matter what you're doing, the f of x plus h minus f of x is always going to be a minus a. In other words, there's no change in the y value, so the numerator is always going to simplify to 0 before you even take the limit. So you have 0 over h, which simplifies to just 0, so the limit is going to be 0, and we've proved that the derivative of a constant is 0. Now, if we look at a couple examples here, if we want to differentiate these constant functions, notice all of these are constants. So part A, if the f of x is the square root of 3, f prime is equal to 0. Part B, if f of x equals negative 1/2, f prime is 0. Even irrational numbers like pi. Pi is a number, not a variable. The derivative of pi is 0. In fact, if you have the function itself is 0, the derivative of 0, the constant 0, is 0. What we're illustrating here is that no matter what the constant is, the derivative is 0. The graph of a constant is always going to be a horizontal line, so its slope is always 0. Therefore, its derivative is always 0. Let's start to talk about the derivative of a power function. When we start to do this, we'll first look at the derivative of the identity function, f of x equals x. This is just a power function with an exponent of 1. So when I say power function, I mean f of x equals x to the n. The identity function is x to the first power. Now, if you look, the graph here is y equals x, and you know from algebra class that a line has a constant slope, a constant rate of change, and the slope of just y equals x, the slope is just 1. So for the identity function, if you're taking the derivative of just x, it's always going to be f prime of x equals 1. Again, if we show the proof here, it's pretty simple. F prime of x equals, so I would take limit as h approaches 0. F of x plus h, if you're just plugging that into x, is just going to be x plus h minus f of x, which is just x all over h. Now the x's will cancel, and the h over h is what is left. H over h is just 1, so the limit ends up being 1. Now we have the theorem. If f of x equals x, then f prime is equal to 1. Now let's move on to the squaring function and the cubic function. We've already used the limit definition of the derivative to differentiate both of those in a previous lesson, and here's what we came up with. If you have f of x equals x squared, then the derivative was 2x. If you have f of x equals x cubed, then the derivative f prime was 3x squared. You might have noticed a pattern here, and here's the pattern. The derivative of each power function is another power function. Also notice that the exponent of the derivative is 1 less than the original function. So if you look at the cube function, the exponent was 3, its derivative is 2. For the square function, the exponent was 2, its derivative, the exponent, is understood to be 1. And the coefficient of the derivative is equal to the original function's exponent. In other words, for the squaring function, its derivative is 2x, the original exponent was 2. For the cube function, its derivative's coefficient was 3, the original exponent was 3. And that's actually the rule for all power functions. Here's the simple power rule, as we call it. The derivative of x to the n is n times x to the n minus 1. So basically, when you differentiate a power function, the exponent comes down as a coefficient, and the new exponent is 1 less. Let's do a couple examples here. So if we want to differentiate x to the 5th, the derivative is 5x to the 4th. You bring the exponent down as a coefficient, and the new exponent is 1 less. For part B, notice g of x equals x to the 10th. The correct notation, g prime, would be 10x to the 9th. Let's look at the derivative of a constant times a function. So in lots of cases, you're going to have to find derivatives of a function that has a constant multiplying it. Turns out the derivative is simply the constant times the derivative of the function. So essentially, if you have some number times a function, then its derivative is that number times the derivative of the function. So this is the constant multiple rule right here. And here is the rule in kind of simpler notation. This is saying if you're taking the derivative of a constant times a function, that's equal to the constant times the derivative of the function. If I have 5x cubed, then f prime is going to be 5 times the derivative of x cubed, which is 3x squared. So 15x squared. For g of u, g prime of u is going to be negative 1/2 times the derivative of u squared, which is 2u to the first power, and that simplifies to negative u. For this one here, u of x is pi to the 4th x cubed, so u prime. This one sometimes trips students up because they see an exponent on pi to the 4th and they're like, oh no, what do I do? Remember, pi is a constant, and a constant to the 4th power is still a constant. So you multiply that constant, pi to the 4th, times the derivative of the power function of x cubed, which is just 3x squared. Then we can clean this up a little bit. It'd be 3 pi to the 4th x squared. The second part of this is we want to use Desmos to find the derivative of f of x equals x cubed at x equals 2. Now for Desmos, if you type in f prime of x, it will graph the derivative function, but it won't tell you what the actual derivative is. We know it's 3x squared from what we just did a minute ago. However, you can evaluate it at numbers. So f prime of 2 is 12, and we could write f prime of 2 equals 12. But sometimes if you're allowed to use a calculator or Desmos, you can just simply do it. Now, this brings up an important point on the AP exam. If you had this exact question and you were allowed to use Desmos, all you would have to write is the notation f prime of 2 equals 12. You wouldn't have to show the work. You have to include the correct notation. So another important property of differentiation is when functions are added or subtracted. Turns out that the derivative of a sum or difference of two or more functions is the sum or difference of their derivatives. So Basically, if two functions are being added or subtracted, you can add or subtract their derivatives. Here's an example where we're kind of pull this all together and do some of the things that we've already done before. So part A says find the derivative of f of x here. So we're going to use the sum and difference rule, the constant multiple rule, the power rule, and the constant rule. So f prime, if we do the 2x to the fourth, the derivative of x to the fourth is 4x cubed, but the 4 is going to multiply the 2, making this 8, minus the derivative of the squaring function. The 2 comes down, multiplies the 6, and that becomes 12. The new exponent is understood to be 1. You don't have to write the 1. The 2x is just 2 times the derivative of x, which is 1, and then minus the derivative of the constant 2, which is 0. Part B, if we want to find f prime of 2, we would just plug 2 into this function right here. Maybe you get 42. Part C, if I want to find the slope of the tangent line to the graph of f at the point where x equals 1, this is equivalent to saying find the value of the derivative at 1. At 1, if you plug 1 in, it would be 8 minus 12 plus 2, which is negative 2. And this would be the slope of the tangent line. Now, this brings us to part D, which asks us to find the equations of the tangent and normal lines at this point. Remember, we have to use point-slope formula. We know that x equals 1 from the question, and we know that the slope is equal to negative 2. The only thing we need to get now is the actual point, the x comma y. So how we do that is, in order to get the y value when x is 1, you would plug 1 into the function. So f of 1, which is going to give us 2 minus 6 plus 2 minus 2. So that's negative 4. That is not the equation of the tangent line or normal line, obviously. That is the point 1 comma negative 4. So we know that the slope is negative 2, the x1, y1 is 1 comma negative 4. So the tangent line is going to be y equals y1, negative 4, plus the slope, negative 2 times x minus x1, which was 1. The normal line is the same thing, except you get the slope of the normal line, which is the opposite reciprocal of the slope of the tangent line. So y equals negative 4 plus 1/2 times x minus 1. And then the last piece is we want to use Desmos to graph f, the point, and those tangent and normal lines on the same screen. So here I have the graph of f. I want to graph the point 1 comma f of 1. It's the point right here. You can zoom in on that. And then the equation of the tangent line, which was y equals negative 4 minus 2 times x minus 1. And the line should just touch the graph at this point. And if we zoom in a lot, we can see that it in fact does. And then the normal line, y equals negative 4 plus 1/2 x minus 1. And we could see down here, if we zoom in, that it looks like the red line intersects the black line at a 90-degree angle, so it's perpendicular. And there we have everything on the same graph. One other thing that you may need to do from time to time is solve equations or inequalities with the derivative of a function. And we'll look at this example here, where we have f of x equals 4x cubed minus 12x squared plus 2. First part is we want to find all points where f has a horizontal tangent line. Well, f has a horizontal tangent line when the derivative is equal to 0. So first we need to differentiate this. F prime of x equals 12x squared. Bring the 3 down, multiplies the 4, subtract 1 from the exponent, minus the 12x squared's derivative would be 24x, and then the plus 2's derivative would just be 0. So we set this equal to 0 and solve for x. So we could factor out a 12 and an x, and that's going to leave x minus 2 equals 0. So this is equal to 0 when either the 12x equals 0 or the x minus 2 equals 0. So that's going to give us x equals 0 and x equals 2. To find the points, we simply plug 0 into the function, so the original function. So it says all points where f, the point would be evaluating f at 0, and you would get 2. So the point is 0, 2. And then when we plug in the other x value, so f of 2, If you plug 2 into the function, you would get negative 14. So that would be the point 2 comma negative 14. So this is all part A. For part B, we want to find where f prime is greater than 0 and f prime is less than 0. So if we look at f prime again, I'm going to take the factored form, which is 12x times x minus 2. Now, in order to solve these inequalities, we're going to use the zeros of f that we got from part A, so when x is 0 and 2, and make a table using the intervals that would result from that. So the first interval we would have would be from negative infinity to 0, then from 0 to 2, and then from 2 to infinity. Now, if we look at the sign of f prime on those intervals, that's going to be helpful. So if we pick any number between negative infinity and 0 and plug it into the derivative, it's always going to have the same sign. This is kind of applying the intermediate value theorem, which basically says if a function is continuous, then it won't change sign without passing through 0. We found the 2 points where the function equals 0, so we know that the points before, between, and after, it would have to have the same sign. So we just pick any number on this first interval. Let's pick negative 1. If you plug it in, you're not so much concerned with the actual numerical value, but whether it's positive or negative. And remember, we're plugging this into f prime. If you plug negative 1 into f prime, you would have 12 times negative 1 times negative 1 minus 2, which ends up being positive. Then you pick any number between 0 and 2. We'll pick 1. You're going to end up with a negative number for f prime. And then the final interval from 2 to infinity, pick any number. I'd pick like 3 or 10, something easy, plug it in, you'll get a positive value. Now, it's not always going to alternate signs like this, where you have plus, minus, plus. So don't think if you get the sign of the first one, then it's just going to alternate from there. Our conclusion is that f prime is greater than 0 on the intervals negative infinity to 0 and 2 to infinity. F prime is negative on the interval 0 to 2. And I just want to show you this in Desmos so you could see what it looks like. So here's the graph, and we notice that at x equals 0, you had a horizontal tangent, and at x equals 2, you have a horizontal tangent. Notice that before x equals 0, the graph is increasing, which means the slope's going to be positive, so the derivative is greater than 0. Then the interval from 0 to 2 on the x-axis, the function is decreasing, so it has a negative slope, which means the derivative should be negative. And then after x equals 2, the function changes again to increasing, which indicates a positive slope and a positive derivative. Well, guys, that's it for this video. Hope that was helpful to you. Reach out if you have any questions, and take care.